Hi everyone. No time on the video. Okay. So first, just I want to clarify that you don't have to submit your work for exercise 1. Exercise 1 is the in-class exercise. So just work hard during the class, and you don't really have to submit, at least for exercise 1. Do you have any questions on the quizzes or the lecture for the last week? Okay. So today, I want to continue chapter 1. We basically discussed the matrices and arrays and data frames and maybe apply functions. Those are very important feature for matrix languages such as R, Python, MATLAB, and other languages. Okay, so I will share the screen. Oh, I got one chat. Hi, this is, yeah, I looked into my, okay, sure. Yeah, so yeah, I will check the attendance based on your name. So just make sure that your name appear in the Zoom. So if your brother's name or your parents' name are on the screen, then I have trouble to check. But as long as your name is on screen, that's fine. Okay, so and hopefully we will do exercise the problem 2 of the exercise after I explain several slides. Okay, so I think this gives some answers for the future questions. Yeah, so the most statistical inferences, such as regression analysis and analysis of variance, are better described when we use matrix representation. So basically, statistics is to deal with the spreadsheets of data. So we have maybe the variables in columns, and we have observations on rows. So we have the spreadsheets of data set. And we have to come up with a method to process all the data as one batch. So that is basically a matrix. So that's why the matrix operations are very important in applied statistics. And statistical languages such as R, S+, MATLAB, GAUSS, OX, and some other languages that specialize in matrix calculation. So sometimes these languages are called matrix languages. So basically it specializes in doing matrix operations very quickly so that it's efficient in statistical analysis. So if you got used to R, then probably it doesn't take much time to get used to other languages such as MATLAB, GAUSS, OX, and maybe Julia and some other languages. Yeah, S+ is commercial version of R. Actually, the S+ was developed earlier than R. And then R basically was developed as a clone of S+. So basically everything is the same. Maybe slightly different in terms of some available options and some other some of the functions, but mostly the same. Okay. So these days, it's even possible to make the ChatGPT to translate the Python code to R and so on. I don't know how accurate it is, but that's possible. Okay, so now that we discuss the matrix operations. And again, these codes are basically the same as the slides in chapter 1. So I don't upload these codes, but you can check later with our slides. Okay, so at first we have to, declare the matrices. So generating matrices. Yes. So the one way to declare a matrix is using the matrix function. So matrix 1 to 6, again, 1 colon 6, this is a sequence from 1 to 6. If just I type 1 to 6, that is a vector. Maybe I can show you. So this is just a vector. But if we put this sequence of numbers in the matrix function with some options, number of rows 2 and the number of columns 3, then you can see the matrix A as this. So this is at least one way to generate a matrix. And 1 to 6 are put in this way. So at first, the first column is filled. So the first column, so 1 and 2, and the second column, 3 and 4, and third column, 5 and 6. This is the one way to generate matrix. If you wanna, so upper arrow that allows you to generate the same code again. So then, okay, so suppose that we wanna make a matrix of 1, 2, 3, 4, 5, 6, rather than 1, 3, 5, and 2, 4, 6. You can specify the option, the by row is equal to true or T. Then you can generate matrix by row. So 1, 2, 3, fill the first row, and 4, 5, 6 fill the second row. So in this way, we can generate the matrix. And sometimes even some arguments are missing, still you can make a matrix. For example, matrix 1, 2, 6, and only we specify number of rows. Then still the same, because the number of rows is equal to 2, that implies the number of columns is equal to 3. So you can get the same result in this way. And actually, anyway, we need the number of rows and number of columns. So if you just type the comma 2, comma 3 in this way, still that you can make the same matrix. But you have to remember correctly that you have, first argument is the numbers to be filled. Second number is the number of rows, and the third one is the number of columns. It's safer to write n row is equal to 2 and n column is n-col is equal to 3. Yeah, and yeah, sometimes you want to make just a matrix with all NAs. So I usually generate this matrix. But yeah, you can do whatever you want. And often it's useful to know this function, the number of rows of A and number of columns of A. Especially for larger matrices, often you want to check the number of rows and the number of columns. And later, we discussed how to manipulate the rows and the columns. For example, we want to multiply 1 by the first column and multiply 2 to the each number of the second column, and multiply 3 to the third column. Then we have to use some loop, and we want to do some operations from like I is equal to 1, 2, 3, and for something. So so in such a case, often we have to count the number of rows and the number of columns. So these functions are extremely useful. And also the dimension of A, this is also useful. We have 2 rows and 3 columns, and this returns 2 numbers as a vector. So the first element is the number of rows, and the second element is number of columns. And another function, row of A, it returns this matrix. So just the first rows are filled with ones and the second rows are filled with twos. I don't use this function often. Maybe some people like to use it. I think probably these functions are also used in for loops. Do you have any questions so far?
Professor?
Yep.
So, what's the reason again for inputting NA into the matrix?
Actually, no reasons, but often when I create some matrix, after creating A, I fill out these numbers later. So for example, we calculate something. So for example, the 1 times 1 is here, 2 times 1 is here, and so on. In such a case, if I made the erroneous code, that actually it does not return the answer. So if we see NA, I can immediately see that I failed to fill out these columns. So in such a case, this matrix is a kind of the safe matrix as the initial state. For example, the 4. Okay, so this is just one example, but the I is in 1 to 2. A of I is equal to 1 or something. Okay. Then after we see this, actually I made a code that fill out 1 in the first column and the second column. But now we can see that I missed to fill out any numbers in the third column. So in this case, sometimes, so this NA matrix is a good matrix to start with, because when we see NA, we see that we haven't done anything on A.
Okay, gotcha.
Yeah. So usually when I create some matrix A and after that I fill out the elements, usually I create the NA matrix first. But that is just a matter of preference. You can make a matrix of zeros or a matrix of ones. Or maybe matrix of 99s. And how to extract elements in matrix? Maybe once again, I define matrix A as 1 to 6, this one, and A 2 colon 2 comma 2, sorry, the A bracket 2 comma 2. So this returns the two elements, the second row and the second column element of A. And if we type the A comma nothing, what happens? Actually, this nothing means that we select all columns. We have 3 columns. So this is the same as the 1, 1, 3. So 1, 3, 5. And the same thing for rows. If you just specify second column, so it selects all rows. We have 2 rows, so this. But actually, the R does not distinguish row vector and column vector. So that's why it returns just 3, 4 as a vector, I mean, 2-dimensional vector. So 3, 4 is actually, in some sense, the 2-by-1 matrix, not 1-by-2 matrix, but the R does not distinguish the row vectors and the column vectors. So this may be sometimes convenient, sometimes confusing. Okay, so suppose that we want to select the first column and the third column of matrix A. So how to do that? Then remember that to declare a vector, that we can use the C parenthesis. So C parenthesis 1, 3 parenthesis. So this is a vector of 1 and 3. So in this way, we can extract the first column and third column of the matrix. And actually, this is the first row. So this is the first row, first column, and the first row, third column. So in this way, we can freely select any elements. And once again, this, if you want to modify the matrix, you can specify the in this way, then this 100 has been changed. This, the 2/3, the second row, the third column has been changed to 100. Any questions so far? Yeah, so if we don't specify anything, that means that we select all columns or all rows. So this is the same as A. Okay, so next, okay, so sometimes we have some vectors, then we want to combine vectors to make a matrix. So vectors to a matrix. So suppose that we have a vector W. This may be the weight of the 3 babies in kilogram. And another vector H. H is height of 3 babies in centimeter. Okay, so we have the W and H, and we want to make a matrix based on these 2 columns. Suppose W is the first column and H is the second column of the matrix. Then we can use the cbind function to generate the matrix. So cbind of this is this. So this is 3x2 matrix. And actually the first column is named as W and the second column is named as H. Basically this is just the same as the matrix we have created. Just we have names for columns. And if we want to combine W and H as row vectors, then we can use the rbind function. So row bind function, then we can see the first row becomes W and the second row becomes H. Yeah, you can name this, for example, suppose this is a matrix B, and you can name the columns of B. I think this is called call names function, maybe. Yeah, call names function. Then you can see, for example, if these 3 babies' names are Andy and Bob and the Casey, then we can get this. So we can name the columns and we can name rows. Sometimes it's convenient to see the results. Also convenient when we make some programming. Yeah, and it was, okay, so just we generated matrices, but now that we do matrix operations, calculations. Yeah, so, okay. Suppose A is a matrix of 1, 2, and 3, 4. So the first row is 1, 2, second row is 3, 4. So this is 2x2 matrix. A is this. And suppose B is this matrix with the 3, 0, and 0, 2. So the first row is 3 and 0, and the second row is 0 and 2. So B is this matrix. So you can calculate, for example, A plus B addition. So this is component-wise addition. 1 plus 3 is 4, and 3 plus 0 is 3, and maybe 4 plus 2 is 6. So this is addition. And A minus B in the same way. So component-wise, for example, 1 minus 3 is -2. So A minus B is this. So this is simple. And next, slightly more complicated. Actually, this isn't very complicated, but the A times B. So it sounds like matrix product, but actually this is component-wise product. Sorry, the product. So you can see that the A is 1, 2, 3, 4, and B is 3, 0, 0, 3. So you can see the 1 times 3 appears here, and 1, 2. So 2 times 0 appears here, and the 1, 2, 3, 4. So 4 times 2 appears here. So this is component-wise product, not matrix product. And how to calculate the matrix product? That is slightly more complicated symbol. A, percentage, the asterisk percentage, B. So this is matrix product. Matrix product. Remember that A is this and B is this. So for example, how to get this 8, that is this inner product of this vector 1, 2, and multiply by B. A is 1, oh, sorry, to get 8, the second row, so the 3, 4 is the vector, and the second column of B is 0, 2. So inner product of 3, 4, and 0, 2. So 3 times 0 plus 4 times 2. So that is 8. So you can see matrix product is this. So this is the sign, the symbol for matrix product. It's slightly, complicated combination of symbols, but this is matrix product. And how about inverse matrix? That is solve of A. This is also somewhat complicated, so, but A. So if you multiply this matrix with A, that becomes basically identity matrix. You can see this is, the 4.44 times 10 to the power negative 16. So that is almost 0. So we have some rounding error, but except for rounding error, that we have 0 here. And here also 0, negative 5.55 times the 10 to the power negative 17. That is almost 0. And here, actually, 1 times 10 to the power 0, that is 1. And this is 1. So I don't know what logic makes this rounding error, but this basically becomes identity matrix. And another way is the same. So if A multiplied by the solve of A, this is again slightly different number, but this is still the 1001 identity matrix. Any questions?
I have a question.
Yeah, sure.
How about matrix exponentiation?
Mm-hmm.
Do we have that?
Yeah. Actually, I forgot the exact function, but yes, there are several ways, and the matrix. I forgot the name. The default R package does not have the power of A, but if you import some library, yeah, I think the some exponent of A is calculated. And also you can use the eigenvectors of A. We will study it later to calculate the exponent of A. And maybe I think that this kind of question is appear in the quiz. For example, how to calculate the A to the power 100. So actually the R has some function, but it's not, so you don't really have to calculate matrix product 99 times. So suppose we want to get A to the 100. Maybe at first A square we can calculate, then we can get the A to the fourth power next, and maybe A eighth next, and so on. Then you can save some time. So there are several ways. Yeah. Exponent of A, yes. I think some optional package can do that. Some optional package can do that. Yeah. Sorry, I couldn't remember the exact function, but yeah, I think I have seen that function before. Other questions? Sorry, for example, if we want to calculate the A100, so this is one good, the mathematics quiz. So as long as you calculate just the exponent of, the product of product in this way, you can actually calculate the A to the power 100 faster. a to the power 64 can be calculated by just calculating matrix product 6 times, not 63 times. So A100 is equal to A 60. A to the 100th power is the A 64th power, and the A 32nd power, and the A to the 4th power. So that is the A100. So you can get this. It's extremely large numbers, but yeah, there are several tricks even if we don't have exponential function for matrix A. Yeah, so next, the vector and the matrix. We have A here, and suppose that X is a vector, maybe uppercase, so 1, 2. So if you want to calculate the matrix product of A and X, or product of A and the vector X, then you can just use this matrix product. And actually, we can do X by A as well. So in this case, the first example, X is regarded as column vector. So a vector of 1, 2. So for example, the first element 5 comes from 1 times 1 plus 2 times 2. 11 comes from 3 times 1 plus 4 times 2. So that is 11. And the second code, this is X as row vector and the X times A. So you can calculate the X times A as 1 times 1 plus 3 times 2. So that is 7. So again, the R does not distinguish the row vectors and the column vectors. So R interpolate automatically X as column vector in the first code and row vector in the second code. Any questions? So we have to be careful to deal with vectors. Sometimes we expect something else, but the change the rows and the columns. Row vector into column vector. Okay, so now the more basic matrices. So suppose that we want to get the identity matrix, how to generate it. Identity matrix can be generated by diagonal, DIAG function. So diagonal 2, this, diagonal 3, this. And also, if you put the vectors such as 1, 3, 5, then we can make a diagonal matrix with elements 1, 3, 5. And okay, so A is this vector, and also the transposed matrix of A can be generated by T of A. So this is pretty short code. So 1, 3, 2, 4. And the determinant of A is calculated by dt of A. So this is basically 1 times 4, the product of the this diagonal term, minus 2 times 3. 3 and the larger matrices, the definition is more complicated, but the determinant of A is negative 2. Any questions so far? Okay, good. And the next, eigenvectors. Eigenvectors will appear in the quiz also. And the eigenvectors is obtained by eigen of A. And the E. And it returns this so-called list. So basically the output have the two objects. One is this vector, the so-called eigenvalues, and the second is the eigenvectors. So this means that this first vector, the first element is negative 0.41 and the second element is negative 0.90. So this vector, if we multiply A by this vector, this column vector, so this vector is just multiplied by the 5.37. So eigenvector is the vector whose direction does not change after multiplying with A, after multiplied by A. So the so if we calculate the A times this vector, that we get the 5.37 times the same vector. Maybe we can okay, so negative 0.4159736, okay, and negative 0.9093767, then we get this vector, and this negative 2.23 is just 5.37 times larger than negative 0.41, and the negative 4.88 is the 5.37 times negative 0.909. So we can double check this, the 5.37 times this vector. So we get the same answer, maybe with some rounding errors. And the same thing for the second one. So if you multiply matrix A and this second vector, the negative 0.82 and 0.56, then this vector becomes just negative 0.37 times larger than the original vector. So the vector whose direction does not change plays important role in linear algebra and also in statistics. So these are important if you want to study more statistics later. So it can be used to calculate the exponent of A, because if you multiply A to the 100th power of this vector, then that is just the original vector times the 5.37 to the power 100. So it's easy to calculate. It's very quick to calculate the product. And based on these two eigenvectors, that we can actually calculate the A to the power 100 directly without multiplying A many times. Any questions? Yeah, and okay, so the output is this, but sometimes we want to extract this, number. So these numbers, maybe this vector as well, and also this matrix, or maybe the first column as a vector. So how to extract those information? Okay, so we name entire quantity as E. So if we type E $sign vectors, then we get the the set of eigenvectors. If we want to extract just first eigenvectors, the first eigenvector, then you can type just the first column. Then you can get this as a vector. So to multiply A by this eigenvector, then you can just type this. Then you don't really have to type numbers again. Then you can verify that this result. So if this is too long, then too lengthy, then you can rename this as, for example, X. Yeah. Yeah, so this vector is just 5.37 times larger than this vector. So the ratio of these two numbers is the same as the ratio of these two numbers. So that is the meaning of eigenvectors. Any questions so far? Yeah, if you couldn't remember what the eigenvectors are, just check with the linear algebra textbook. But in this course, the eigenvectors, they do not appear too often. So maybe if we take stat 5820, we do the principal component analysis, then you will need more eigenvectors. Okay, and we can. Yeah, maybe we go back to the slide. We have already discussed this for column names, but when we have matrix A, then we can name those rows and columns by using this row names function and col names function. So this function can be used when you want to assign row names, and also it can be used to extract the information of row names. So later we study how to code more complicated commands. And for example, if we wanna extract the Alex's weight, then we can refer these names to see which rows have information for Alex. So sometimes these kind of names are useful for coding. Of course, it's good to they read the data, but also it can be used for coding. So row names function and call names function. Yeah. So sometimes, if you don't know this, then you are confused whether this is matrix or some other object, but this is just a matrix with names. Okay, and so next is array. So vector is an object with one index, and the matrix has two indices, and the array may have the more than two indices, 3, 4, 5. I don't know how many is possible, but sometimes it's useful to generate array with the 3 dimensions. So how to generate this? And we can use array function, and you can specify elements. We have 24 elements, 1 to 24. And we have to specify the dimension for the first index and the second index and the third index. And here I generate 3, 4, 2. So 3 by 4 by 2 array. So in total, we have 24 elements. 3 by 4 by 2 is 24. So A is an array. And okay, so what is A? A is this object. So A is a bit kind of two set of the set of two matrices, and the first matrix is this, and the second matrix is this. You can see this as two matrices. So and the first matrix is this, so 3 by 4 matrix. So this is the first row, and this is, for example, second column, and this is kind of the first matrix. And this is the second one. So this is, for example, the third row and fourth column, and the second matrix. So in this way, we can generate array with more than 2 dimensions. And at first, the first column is filled out, and then second column of the first matrix, and the third column and the fourth column, and so on. Yeah, we don't use this too many times, but sometimes for complicated coding, this may be useful. And we have the transpose function for this array. A parm maybe permutation, and the A parm function of A, and you can we have to specify these indices. So we changed the second and first indices. So we interchange the second and first, so that we interchange the rows and the columns. So this A parm is this. Yeah, so to be exact, the second index of the original object becomes first object. The first index for the original object becomes second object, and so on. second index, and so on. Yeah. Any questions? Yeah, we don't use this too often. I haven't used this for maybe 10 years, but sometimes it's useful. You may find useful in some complicated coding, especially if we have the spreadsheets, the multiple spreadsheets with the same format. Then sometimes it's good to put everything in one array. Then it's good to manipulate it. Okay, so next we study list. Yeah, so sometimes we want to put the multiple objects within one object. So one good example is the output of eigen function. So this E is actually a list with the two sub-objects. So first sub-object is this values, and second sub-object is the vectors. So to be exact, the first object is the two-dimensional vector, and the second object is basically 2x2 matrix. So we have two objects, and each object has a name. So basically this is called a list. So it's not a vector, it's not a matrix, but this is a list. So we consider another list. Suppose that we want to make a schedule for classes. So first object in the list there will be the instructor, and the second object is time. So maybe in this class, it started at 6:30, right? So 6:30, so the start time and end time. So this vector, and once again, the Tuesday and Thursday, we have this vector again. So suppose that we have the time for classes and maybe row names of time is maybe the Tuesday and the Thursday. And the call names of time. First one is start. Probably this single quotation also work. And suppose we want to combine these two information as the S5030. So we make a list of instructor and time. Maybe we name instructor as just INST and time as TIME. Sorry, the instructor does not exist in, the int. Yes, I missed S, so maybe just this. Okay, and S5030, then it returns this. So to make a list, one way is to generate the multiple objects. Then we use this list function to declare a new list. So in the computer, we have basically three objects. We have created three objects. The first object is instructor. Actually, I misspelled it. So instructor and time. So these two objects, and then we generated stat 5030. And within this object, we have the sub-object. One is INST and the other is time. So this is a little complicated. So probably you want to remove the first two object because interact. Yeah. Yeah. So you can see the first the named the wrong name. So I should write the INTRUCTOR, but I include S, so that it returns a warning message. But warning message isn't an error message. So actually the R eliminated these two objects if these exist. And actually the R already eliminated the time object here. So once again, I deleted object and the interactor has been deleted, but the time has already been removed. So that we got another warning message. But now that we eliminated both time and interactor. So now we only have S5030 object. Yeah. If we don't remove these two objects, that we are sometimes confused with this time and this time. So usually it's a good custom to delete this after you created this list. Okay, so this is a list. So list consists of multiple objects, and we can access to the list by typing the $sign. So S5030 INST, then you can get this. And also we can get this by double bracket 1. We get the same answer. Single bracket, it's similar, but the single bracket, still the S5030 is a list with only one object. So list of one object and the object itself is different, right? So this is just, this one character, one sequence of characters, but this is a list of one sequence of character. So for example, S5030 double bracket 1. So this is already this the one sequence of characters or just a vector of one element. So you can, for example, extract the first element of this vector. But this one that behaves differently because this is list, okay, and we specified just the first element of list. That is still the INST, right? F5030 single bracket 1. This is a list consisting of one object that is INST. So the first element of that is, okay, first object of that. So the first object is still INST. So that's a slight difference. And the second object that we can get this, but for example, if you specify the second row, second column, it returns an error because this one is recognized as just, list of one object. List of one object. So that we should have only one index, which indicates just the number, the order of the list. So just the first element of that list. And actually this list only have one element. So if we type, for example, 1, so this returns this object, but if we type 2, then, okay, so this list only have one object. So the second object does not exist, so it returns null. But if we put the double bracket, then we can extract, for example, the second row, second column of this matrix. Because this is matrix. S5030 double bracket 2 is a matrix. So we can specify the row number and the column number to extract the specific information. Yeah, maybe we can do this also by doing this. Yeah. So there will be a quiz there for this. Okay, so any questions on lists? Okay. And some examples for list. Maybe I will show the slides to just save some time. So sometimes a function returns a complicated list as an output. So we have the midterm 1 scores for several students and the midterm 2 scores for several for the same students. And we want to see if midterm 1 score is different from midterm 2 significantly. And I mean, the mean midterm 1 score is significantly different from mean midterm 2 score. Then we can use the t.test function to do that. And then actually this t.test, maybe I have to still code it, sorry. Maybe mid1 score that we just type randomly, maybe numbers. And midterm 2 scores, it sounds more difficult, and maybe like 70 and 90 and 95 or something like that. Okay, then midterm 1 minus midterm 2 is this, and we can use the t.test. We can use t.test function if the mean scores are significantly different. Then it returns this output. So it's a complicated output. We have many information, some verbal information, and also some numbers, t-statistic, and the degrees of freedom of the test, and the p-value, and the confidence interval, and the sample mean of the difference. Yeah. But actually, if you access, for example, if we name this as the TT, and we extract first element. Actually, this TT, first element of TT is the t-statistic. Yep. So this output itself is coded with some beautification, but basically the structure of this object is that the first element of the object is t-statistic, and the second element of the statistic, the second object in this list, the TT, is a parameter, degrees of freedom, and it's named as parameter. And the third object is p-value. The fourth object is confidence interval. And actually, this is a set of maybe 2 objects. Yeah, so this object includes 2 sub-objects. First is confidence interval, which is a vector of 2 numbers, vector with 2 numbers. And the second one is the just a vector of 1 number, that is confidence level. And 5, this is the mean of x, and the 6, not exactly sure, but I think that this is some null hypothesis. And 7, standard error. And 8, the type of the test. 9, the type of the test again. And the 10, some names. So basically, this TT object have 10, so TT list, the list of TT have 10 objects, 10 sub-objects. And the 10 sub-objects are accessed by either typing the bracket or double bracket number, or you can specify these names to get it. For example, if you want to extract t-statistic, then you can type TT $statistic. Then you can get 2.25. So for example, if you multiply this by 2, then you can do it this way. Yep. So just I want to explain that the some output of a function is a complicated list. We will study t-test later in chapter maybe 4 or 5. Any questions? And the next one is the DataFrame. So DataFrame is the very popular type of list. DataFrame is a special case of list. And for example, we have the 3 vectors, the gender, height, and weight. So gender is vector, maybe character vector. Maybe I want to make it as a factor later. That's the okay. And the second object is height. Height is maybe there are these numbers, maybe height in centimeter. This is a numeric vector. And weight of these, the 5. These four people. then we can declare the data frame. Data frame is a special case of list, but it should have the vectors with same length. So these three vectors are all, three vectors all have 4 elements. So if we put in a spreadsheet, it's a kind of matrix shaped object. So in such a case, that we can declare a data frame. So D is this. Maybe it's good to eliminate these original vectors. Oh, sorry, the height. Okay, yeah. Then now we have the D. So D have basically 3 objects: the gender and height and weight. So D consists of 3 vectors. So D is a list. But even though this is a list, it almost looks like a matrix because all vectors have the same length. So this is a list. So for example, we can extract gender out of D. But also we can treat this as a matrix sometimes. For example, we can extract the height for the second row. So that is done by D22. So this is basically the grammar for matrices in R, but actually we can access to this element by typing D bracket 22. So the data frame is a list, but sometimes data frame behaves like a matrix. Sometimes not. And what's the difference between data frame and matrix? Of course, it's different because the data frame is a list, but also the list the data frame allows the different types of vectors, different types of columns. Matrix, everything should be the same. So everything should be numeric or everything should be character. So we cannot mix those two, but the data frame, we can do whatever we want. And if we type structure of D, then we can get this. Yeah, so this is the structure of D. So you can see the first column is character and the second column is height and third column is weight. So if we want to make this first one as factors, the factor D gender, maybe we as factor. So D $gender, we redefine this as a factor. Then structure of D is this. Yeah, actually in slice, originally this result is factor numeric. So old versions of R has function to automatically change characters to factors, but that is a kind of annoying. So that's why there are changed the default setting of this the data frame, and the character just remains as characters. But if you want to make it as factor, then you can certainly do that by using as.factor function. Yep. Any questions? Okay, so now maybe we do some exercises for just 10 minutes. Sorry, then maybe I got one chat. Oh yeah. I will set up several breakout rooms, so you can discuss the exercise 1, question 2. And I recommend one of you share the screen and discuss the problem. And this time, how many students are there? Maybe 24, 25. Where I can see the number of students. 1, 2. Anyway. So this time we have slightly less number of rooms, maybe 6 rooms. Assign automatically. So just for 10 minutes, you can use the exercise 1 available on the Canvas. Okay, So we open the rooms.
Okay. Oh. Sorry, Professor, if you're trying to talk, you're muted.
I have to check the attendance. Dalvar is here. Ryan? I checked
here.
some. Ryan here? Okay, yeah, sure. And the Alexander, I think here, right? Yeah, okay. And the Maitri, yes. And Caitlin here? Caitlin not here? Okay, not here. And the Jason here and the Katie not here. And Bindir here. Jordan?
Here.
Okay. Sonali here. And Elena not here. And I think the Tamika here. And Ada.
You said Tamika?
Yeah. And
Yes.
Ada here. Okay. And the Tanjanika not here. I think she's never here. Mick here. Mick here. Okay. And Kevin.
I'm here.
Okay, sure.
Here.
Asad not here. Andrea not here. Nicolas Kostakis not here. Okay, great. Yeah. And I think I don't really have much time to explain, but I will share the solutions later. Katie here. Okay. Katie here. Okay, great. Yeah, I will share the screen and the solutions will be available in the website soon, but just I would like to do a little bit. Okay, so question 2. The first question that we have to define the matrix A. So we have to declare matrix and the 900,713 and 265. And 33. So A is this matrix. Then A is done. So B, the obtained matrix product. Matrix product is obtained by this. So this is the A times A. So obtain the A to the negative third power. We have several ways. So for example, we calculate the third power first. Say this as B and solve B. So B is this. So final answer should be this. But maybe you can do also the solve A. This is another way to do this because A to the negative third power is negative A inverse times A inverse times A inverse. Anyway, the result is the same. So this is C. So D, the eigenvectors. So basically it asks eigenvectors. So we can use the eigen of A. So we get the 3 eigenvalues, 9 and 7.69 and negative 1.69. So what is the smallest? I find all. Yeah, for all possible numbers. So that is 9 and 7.69 and the negative 1.69. And each vectors 1, 0, 0 corresponds to this the eigenvector. This negative 0.97, negative 0.13, negative 0.15. This corresponds to this eigenvector. And actually, these are unit vectors. For example, the 0.97 square plus 0.138 square plus 0.154 square. So this becomes 1. So we have some rounding errors, but this becomes 1. So this is a unit vector. So question E. So suppose that x is a unit vector and determine x, which maximizes a to the 5th power times x absolute value. So remember that the largest, the eigenvector with largest eigenvalue becomes, larger in size fastest. So that means that this eigenvector, so 1, 0, 0 becomes larger and larger, the fastest. So actually, when x vector is 1, 0, 0, the size of a to the 5th power x is largest, and the size is 9 to the 5th power. So you can do that. So maybe a to the 5th power, maybe just simply, maybe we put in this way. And then we can multiply by 1, 0, 0. So this becomes this large. And f and g, I think I don't have any time to discuss anymore. So I will upload the solutions to the website. Okay, so that's it for today. So see you on Thursday if you don't have questions. If you have questions, just remain online.
Thank you.
See you.
Have a great day.
You too.
Thank
Have a
you.
good day.